everybody. How we all doing? Hopefully everything's running okay right now. I think I'm dropping frames. Yeah, I'm dropping frames big time. Oh yeah. I'm cutting out. Mika, you better back the fuck off. Let's see if this connection issue continues. Hopefully not. No, it is. Yeah, it's cutting in and out. What is going on?
Cables or something?
Well, let me see. Seems to be doing a little better. Let me know if it's like fucking up. Anyway, yeah, how's everybody doing? Chill, play some games, watch some videos, have a good time. As always, suggest stuff to watch and chat. And yeah, let's get into it.
With the success of Artemis 2 under their belt, NASA is carrying a ton of momentum into the next phase of their return to the moon. But that leaves a lot of us wondering, what comes next? Well, the answer is complicated, and it involves one of the biggest competitions ever staged between two titans of American industry. Artemis 3 will push NASA to the absolute limits of what they can achieve, because their place as the global leader in space exploration is no longer guaranteed, and the competition is moving fast. That means that we have a lot of work to get done in a very short amount of time. As soon as the smoke was clear from Artemis 2, NASA began assessing the condition of their mobile launch tower. It had been reinforced and beefed up following some heavy damages from Artemis 1, with the intention of drastically reducing turnaround times between launches of the SLS rocket. All of the critical pieces for Artemis 3 have already been completed: the booster engines, the upper stage, and the Orion spacecraft, so it's just a matter of putting them together, and NASA is not wasting any time. But there is an extra complication in this next phase that's somewhat beyond NASA's control. In order to do Artemis 3, they need more than just the SLS rocket and Orion spacecraft. They need a moon lander. And this is where things get really interesting. So in 2021, SpaceX was awarded a NASA contract to convert their Starship upper stage vehicle into the human landing system for Artemis 3. Now, it's important to remember that at the time, Starship looked like this, a very early prototype that would launch itself a few kilometers up into the sky, then fall back down and try to land. Mostly, it would explode, but after one successful touchdown, SpaceX moved on to this, the Starship Super Heavy, a much bigger and slightly more developed prototype. Over the past 3 years, we've seen progressive iterations of this design complete a variety of test flights that send the upper stage into a suborbital trajectory and result in either the ship failing and coming back down in little pieces, or succeeding and landing itself on the water of the Indian Ocean. Generally, there have been more failures than landings, but it is undeniable that an insane amount of progress has been made, and Starship does get a little closer every time to becoming a functional rocket system. But there's a problem here. While being genuinely amazing and unprecedented in almost every way, progress on developing Starship into a reliable vehicle that can land safely on the moon has been slower than what Elon Musk originally promised. Now, in hindsight, that should have been expected. It's kind of a thing that he does a lot. So in May 2023, just a few days after Starship Super Heavy lifted off for the first time and attempted to reach outer space but lost control and exploded along the way, NASA awarded another moon landing contract, this time to Blue Origin, the Jeff Bezos-owned American rocket maker who at the time was famous for launching wealthy people to the edge of space. But just like SpaceX, they had big ambitions involving their own heavy rocket, the New Glenn, and a landing vehicle called Blue Moon.
Yeah.
Space has always inspired us, from the first rockets leaving Earth to the images of distant planets, to the missions still pushing the boundaries of what's possible. And that sense of inspiration doesn't have to stop when the video ends. That is where Displate comes in. Displate creates premium metal posters designed to capture what you are passionate about, whether that's space exploration, science, or the future of humanity. The prints are made on durable steel so the colors stay vibrant and detailed for years. There are over 2 million designs available, including officially licensed artwork and original creations from artists around the world. And if you want something truly personal, you can even upload your own image and turn it into a custom metal poster. What I really like is how easy they are to set up. No drilling, no tools, no damage to your walls. The magnet mounting system takes seconds, and you can swap designs anytime. It's a simple way to bring that sense of exploration into your everyday space. If you want to check it out, use the link in the description. The discount is applied automatically, or you can use my code at checkout. You'll get 26% off 1 Displate, 31% off 2, and 36% off 3 or more. Start building your own space, one story at a time. So this is where it becomes a battle of the titans, because in January 2025, Blue Origin effectively caught up to SpaceX by launching New Glenn for the first time. This was a mostly successful test flight where their booster did end up exploding in mid-air on the way back down. But then in November 2025, they tested New Glenn for a second time, and everything worked according to plan. The upper stage deployed 2 satellites on a path to Mars, and the booster came down for a soft landing on a floating platform. So, given the current state of this race between these 2 companies, NASA has decided that one or both of these moon landers will be tested on Artemis 3. It all depends on who can execute on time, and that time comes in 2027. Now here's what that looks like. Artemis 3 will begin much like what we saw on April 1st, with a new crew of 4 astronauts strapped into their capsule on top of a giant orange rocket. But this time, their destination will not be the moon. That doesn't mean that landing people on the moon has become any less urgent at NASA. They're actually in much more of a hurry than ever before, but it does mean that the path leading up to a moon landing has become much more clear and nuanced. For example, the old plan was to jump straight from Artemis 2, which we all just saw fly around the moon and come straight back home, and then go directly into landing people on the moon on Artemis 3. As far as knowing how they would actually complete the landing, well, they were basically just going to figure that out along the way and hope that it worked when they got there. Not exactly inspiring a whole lot of confidence when people's lives are on the line. So the new plan for Artemis 3 involves testing out a potential lunar lander in space while staying close to the safety of Earth, should anything go wrong. That means alongside the launch of SLS and Orion, there will be 1 or 2 additional giant rockets lifting off. For this example, let's stay positive and assume both lander candidates are ready to go, because then we can show you what it looks like in both scenarios, and that's pretty cool. The first thing to launch will be our moon landers. That means a Starship and a New Glenn. They'll both need to deploy their upper stage lander into a low Earth orbit. Now this is where the first big challenge occurs. Lunar Starship and Blue Moon are so massive that they burn an incredible amount of fuel just by moving themselves from the Earth to the moon. So before they can actually land, they need to refuel in space. Otherwise, they won't have enough to get the astronauts back up off the moon. So as part of Artemis 3, both companies need to demonstrate that they can successfully refuel a spaceship in Earth orbit. For SpaceX, that means launching a second Starship that will act as a fuel tanker. For Blue Origin, that means launching a separate propellant transport vehicle. So now we get 2 more giant rocket launches, followed by an orbital docking and propellant transfer demonstration for both the Lunar Starship and the Blue Moon. Might not sound like a big deal, but no one has ever refueled a ship in space before, so doing 2 at once is a giant leap forward. Now, assuming that all checks out, it is time for the SLS to launch. This will play out the same as Artemis 2, except once the Orion capsule gets to space, it won't be heading for the moon. It will be setting course to rendezvous with their first lander. The first challenge is docking the 2 spacecraft. The lander will be autonomous, but Orion will have a pilot at the controls. This is actually something that they practiced on Artemis 2. There was a mock docking exercise where pilot Victor Glover steered his capsule toward its own spent upper stage engine. In Scenario 1, Orion approaches the Blue Moon from the side and links up with a docking port on the crew cabin at the bottom of the lander. The top sections are all just fuel tanks, and they'll transfer directly into the habitation module. It's not the most spacious interior, but if you look at a size comparison between Blue Moon and the old Apollo lunar module, you can see they are getting quite a bit more room to move around.
Oh yeah.
Scenario 2 looks a bit different. The lunar starship has its docking port in the nose, so once the crew transfers through, they're moving directly into a big, wide-open expanse of a 9-meter wide and several meter tall flight deck. There's a luxurious amount of space in there. Now, in either case, once the crew gets settled, they're getting down to business. That involves a thorough shakedown of the critical systems like life support, power, propulsion, and communications. They're likely to undock the landers, practice some manual control in orbit, and then redock with Orion. The point here is finding any fault that needs to be refined on the next iteration of the vehicle, the one that will actually land people on the moon. Remember that the original plan for Artemis 3 was to have people enter one of these landers for the first time while already in orbit around the moon. That is a bad place to figure out that something isn't working the way it's supposed to. But back to our testing scenario. While inside both landers, the crew will also be trying on their lunar spacesuits in microgravity for the first time. These are made by Axiom Space, and they're a totally new kind of suit, different from what NASA uses on the ISS and different from what was used on the moon back in the day. These should help future moonwalkers to be much more agile and a lot less clumsy looking than their predecessors. These suits have been tested underwater on Earth, which kind of simulates some aspects of outer space. But the real test will be when astronauts take the suits into the airlock of the lander and expose them to the vacuum of space for the first time. NASA expects that all of these exercises will take up to 3 weeks for the crew to complete, so we'll have a lot to look forward to once this gets off the ground. But while we wait for Artemis 3, there's even more action happening right here on Earth. In May 2026, SpaceX will test the Starship version 3 for the first time from their brand new launch pad system at Starbase, Texas. This is what the company believes will be the first non-prototype Starship, the first finished product. This is the vehicle that they believe can take people to the moon. Now, of course, they'll have to build one with all of the interior design features and life support systems to make this giant rocket into a livable space for real people, but they've got a year to figure that out. Over at Blue Origin, they've also got a historic launch scheduled in May, a test flight of the Blue Moon Mark 1 prototype. This is a smaller version of the human landing system Blue Moon. It's designed only to deliver medium-sized cargoes to the lunar surface, and that's the goal for this first test. Get all the way to the moon and touch down safely. If they can pull it off, then that's going to inspire a lot of confidence around NASA, and it transforms Blue Origin from a late arrival to a serious contender. So assuming that both of these companies pull through and we get a successful Artemis 3 with 2 vehicles being tested in Earth orbit, then it's time to move on to yet another epic milestone, an autonomous uncrewed moon landing. Think of it kind of like Artemis 3.5, because once we've verified that the lander is safe for people to live, then we need to see it actually land on the moon successfully. Only then can one company be declared the true winner. And that's still no time to celebrate, because NASA wants to do Artemis 4 within 1 year of Artemis 3. So either SpaceX or Blue Origin needs to be cranking out these landers at a breakneck speed. This is how America is going back to the moon. It's not just to plant another flag and pat themselves on the back for a job well done. This is about total domination of the lunar environment, because there is another great power that's looking to plant their own flag up there. And they're not coming to play around either. China has their own plan for a future moon base, and if you want to see what that's going to look like, then click the box on screen right now.
I want to see what that's going to look like.
China has quickly emerged as a new leader in robotic exploration of the moon. With each successive mission, the Chinese have made unprecedented gains in their ability to reach the surface of the moon with advanced scientific instruments and sample return capabilities. In their most recent lunar excursion, China has made their mark on some of the most valuable real estate that the moon has to offer, and that is just one small step towards a much bigger Chinese presence on the moon that will happen in this decade. On the morning of May the 3rd, a Chinese Long March 5 rocket launched the Chang'e 6 mission, the world's first spacecraft designed to retrieve samples from the moon's far side. About 37 minutes after liftoff, the 8,200 kilogram Chang'e 6 spacecraft stack separated from the rocket, entering its planned orbit of 200 by 380,000 kilometers. This started a complex 53-day mission orchestrating 4 spacecraft, an orbiter, a lander, an ascender, and a re-entry capsule. On May 8th, China's Chang'e 6 spacecraft stack successfully entered an elliptical orbit around our moon, using a 3,000 Newton engine on the orbiter module to perform the braking burn, slowing the spacecraft enough to be captured by the lunar gravity.
Remember that short period of
Shortly
time
after, Chang'e 6
where
deployed
everybody
Pakistan's
worked together in
7-kilogram
space?
CubeSat called iCubeQ in
Those were
orbit,
good times.
making it the country's first mission exploring our cosmic companion. Developed by Pakistan's Institute of Space Technology with aid from China's Shanghai Jiao Tong University, iCubeQ hosts 2 optical cameras and a magnetometer. Scientists hope the orbiter will detect potential signs of water ice on the moon's poles. Now, following a 14-minute descent from an altitude of about 15 kilometers in its lunar orbit, China's Chang'e 6 lander successfully touched down on the moon's far side on June 1st, resting at 153.99 degrees west.
Whenever I see a title like this, I know exactly, like, Heritage Foundation and those kind of groups are behind it. Yeah, I still know who came up with it first. Parents Decide Act is such a manipulative title. Operating system level, I don't know if I agree with that.
Mm. 41.64 degrees south, near the southern rim of the 500-kilometer-wide Apollo impact crater. This marked China's 4th successful landing in 4 attempts. It's also only the 2nd ever far-side lunar touchdown after Chang'e 4. Much like most modern lunar landers, Chang'e 6 used several key technologies to descend onto a safe spot: a variable thrust engine, optical imagery, onboard maps, hover phases to detect hazards, and shock-absorbing crush core legs for the final freefall. Chang'e 6 also used a laser-based LiDAR sensor to map the local landing area in 3D before the final landing phase. This is a sped-up interpolated video from CNSA showing the view from Chang'e 6 during its lunar descent and landing.
Exactly.
Interestingly, CNSA's new release also mentions landing aid from another sensor. To prevent interference to optical sensors by lunar dust during landing, the lander is also equipped with gamma-ray sensors to accurately measure the height through particle rays, ensuring that the engine can be shut down on time and the lander can touch down smoothly on the lunar surface. So in the span of 1 week, Chang'e 6 successfully touched down on the moon's far side, collected up to 2 kilograms of soil and rock samples using a still drill and a movable complementary surface scoop, as well as context-providing lander instruments including cameras, a ground-penetrating radar, and a mineral spectrometer. The lander then used its arm to move the samples to a sealed container, deployed a small 5-kilogram rover to tactically photograph the lander, and launched the samples to lunar orbit as part of an ascent module on June 3rd, which autonomously determined its position and orientation with aid from the Chuichuao-2 Communications Relay Lunar Orbiter, and then docked with the Chang'e 6 orbiter on June 6th, following 4 orbital adjustments, about 30 minutes after which the lunar samples were transferred to the Earth return capsule. On June 21st, the Chang'e 6 orbiter module hosting the sample capsule began its journey towards Earth. When 5,000 kilometers away from Earth on June 25th, the orbiter module released the roughly 300 kilogram re-entry capsule, which later performed a bounced atmospheric re-entry, then safely descended and landed in China's northern Inner Mongolia Autonomous Region. That was one impressive way to perform a very nominal mission, including the orchestration of many modules, the kind that will help China land humans on the moon, which the country hopes to achieve by the end of the decade. China is so far the only nation to have performed robotic rendezvous and docking at the moon. These Chang'e 6 lunar samples are scientifically even more valuable than the previously collected Chang'e 5 samples. Since the Apollo crater is embedded in the moon's largest, deepest, and oldest crater, the 2,500-kilometer-wide South Pole Aitken Basin, the diversity of materials within the Chang'e 6 samples could help scientists worldwide solve a whole host of moon mysteries, such as understanding the distinct lunar farside volcanism and why the far side is so enigmatically different from the familiar near side, which is necessary to understand not just the moon's evolution, but that of our solar system as well. Since Chang'e 6's surface mission was on the moon's far side, the side we can't see from Earth, mission operators commanded the lander and received data from it via the recently launched Chuichuao-2 Relay Orbiter. This orbiter will also relay communications for China's upcoming Chang'e 7 and Chang'e 8 landers. More on both of those missions in a minute, which are currently targeting launches in 2026 and 2028, respectively. The Chuichuao-2 mission is testing and verifying technologies that will feed into the upcoming Chuichuao satellite constellation, the world's first lunar navigation and communications service. The Chuichuao constellation could also provide communication support for China's first crewed moon landing, currently targeting a launch by 2030. The Chang'e 6 lander carried 3 instruments from Europe: the negative ions at the lunar surface payload from ESA and the Swedish Institute for Space Physics, the French Space Agency's detection of outgassing radon detector, and Italy-based SCF Labs' INRRI retroflector. ESA's NILS already detected negatively charged particles on the moon's far side, a world first. These particles are produced due to highly energetic solar wind particles slamming the moon's surface and kicking up secondary particles. NILS is the first European instrument to operate from the moon's surface and is also Europe's first such collaboration with China. Beyond that, ESA has been providing ground station tracking and orbital confirmation support for Chang'e 6, similar to how ESA has been helping ISRO's Chandrayaan missions. The DORN instrument was intended to measure the noble gas radon leaking out of the moon's surface, which could provide independent evidence that our moon and Earth do indeed have a common origin. DORN also studied volatile gases, such as water vapor in the moon's exosphere. The INRI retroflector will reflect laser pulses from lunar orbiters in the future to get precise distance measurements and aid their navigation. CNSA is targeting the launch of their Chang'e 7 lander and orbiter in 2026. The lander, after touching down in one of the key identified landing regions on the moon's south pole, will deploy a rover and 1 or 2 hoppers. Similar to the NASA Viper and JAXA ISRO LUPEX missions, one of the Chang'e 7 elements will use a drill to sample materials in nearby permanently shadowed areas from varying depths. These will be fed into a heating furnace for the onboard lunar water molecule analyzer to detect water ice and other volatile resources like ammonia. Chang'e 7 will also carry a ground-penetrating radar to map the local subsurface, make local magnetic field measurements, and carry spectrometers to measure the composition of the local lunar material. In a similar vein to the seismometers selected to fly to the moon on the NASA-funded Draper-led CLIPS mission and Artemis 3, Chang'e 7 will have one to help scientists better understand the lunar interior and also constrain the rate of seismic activity and the amount of micrometeorite impacts on the lunar south pole, which will help safely plan lengthier crewed missions to the region in the future. Also, on April 24th, CNSA announced that Chang'e 7 will carry 6 international scientific instruments. The orbiter will carry a hyperspectral mineral mapping camera made by Egypt and Bahrain, a 3-kilogram instrument duo from Thailand to study solar storms and cosmic rays, and a Swiss-aided radiation monitor to measure incoming and outgoing radiation to and from Earth. For Egypt, Bahrain, and Thailand, this mission represents their first study of the moon. On the other hand, the lander will carry a Russian lunar dust and plasma analyzer, a telescope from the International Lunar Observatory Association, and another reflector from Italy-based SCF Lab, just like Chang'e 6. The Chang'e 7 lander was supposed to carry UAE's second lunar rover too, but the partnership was apparently blocked by the US export control rules. Now, some might say that the Chang'e 7 candidate landing site near Shackleton Crater is the same as what NASA desires for the Artemis 3 crewed moon landing mission. Gizmodo titled this article "China Oversteps NASA in Choosing Coveted Shackleton Crater for its Moonlander." So did China really choose the same lunar landing sites as the US? Well, that's questionable. Firstly, it was always likely and known that the robotic Chang'e 7 would land on the moon's south pole before the crewed Artemis 3 mission did. So can we even call the former to be choosing the same site as the latter? Artemis 3 has 13 candidate landing zones at the moment, which is not exactly a selection. More importantly, Shackleton is a big 21-kilometer wide crater, and the number of mission-favorable areas on the rim and nearby ridges are relatively plentiful. Even if both missions ultimately chose Shackleton as the main landing region, they may be reasonably far away, not just in time, but in space too. While yes, the water-hosting lunar south pole not being a massive place could eventually mean potential contest between countries and companies for some common sites, but much before that comes the fact that there are purely engineering and scientific factors that make landing site selections converge to some locations. For example, the sun perpetually circling the lunar polar horizon, coupled with rocky terrain, automatically render high-altitude areas desirable power-wise for touchdown, which is what most lunar polar missions end up converging to. Scientists and engineers on both sides of the ocean understand these technical factors, but they aren't the only ones in the space chain. Such factors should be considered first before jumping the gun with policy recommendations and changes that are based on shallow narratives. Again, these could also adversely affect international cooperation and collaboration. Ultimately, alarmist propaganda also makes discussing the real challenges more difficult. Now, after CNSA's upcoming Chang'e 7 mission helps scientists get a tactile sense of the true nature and accessibility of water ice deposits on the moon's south pole, the agency will follow it up with Chang'e 8 2 years later. Launching on a Long March 5 rocket in 2028, the mission will comprise a lander, a rover, and an operation robot to collectively explore with 14 instruments the local geology and environment. Most crucially, with Chang'e 8, CNSA aims to test technologies most relevant to begin sending crew to the moon at the end of the decade. As Lingshin reported, CNSA called for domestic proposals for 9 out of 14 of the Chang'e 8 instruments in February. One such payload on the lander will melt lunar soil and transform it via 3D printing into parts that can be assembled. Another instrument will monitor and inspect this process. Chang'e 8's approximately 100-kilogram operation robot, which will move around quickly by lunar rover standards, will carry the 3D printed parts from the lander to a working area and assemble basic structures as a demonstration of in-situ utilization of lunar resources. The robot will also fetch rock and soil samples for the lander spectrometers to determine their chemical composition, which will likely include water ice. CNSA might leave some samples on the moon for future missions to retrieve them and bring them to Earth. Just like Chang'e 7, Chang'e 8 will have a seismometer to help scientists better understand the lunar interior and also constrain the rate of seismic activity and amount of micrometeorite impacts on the lunar South Pole, which will help safely plan long-duration crewed missions to the region in the future. What's also notable about Chang'e 8 is that China has further increased the scope of international contributions. While Chang'e 6 and 7 each offer space for 15 to 20 kilograms of international instruments, China has been accepting proposals for scientific instruments, technology payloads, and even system-level contributions equaling up to 200 kilograms for Chang'e 8. As Andrew Jones reported, CNSA is expected to announce selections for the same by Q3 this year. China has made systematic progress with their moon missions. The successful lunar orbiters Chang'e 1 and Chang'e 2 led to the moon landing of Chang'e 3 in 2013, which in turn led to the far-side lunar landing of Chang'e 4 later in the decade. CNSA once again upped engineering complexity by bringing lunar samples to Earth with Chang'e 5 in 2020, and then did it again with Chang'e 6, collecting the first ever samples from the moon's enigmatically distinct far side. And with Chang'e 7 aiming to provide scientists with a tactile sense of the true nature and accessibility of water ice deposits on the moon's south pole, followed by Chang'e 8, demonstrating technologies like building 3D printed bricks out of lunar soil. The two missions will allow China to continue charting a clear path that leads to putting humans on the moon by the end of the decade, work on which also seems to be progressing well. At a recent press conference, leading officials from the China Manned Space Engineering Office said that elements of China's first crewed lunar landing mission have progressed into prototype production and test stages. While not yet announced, it can be expected that China will conduct at least one uncrewed lunar landing and a crewed lunar orbital flight before attempting to land humans on the surface. China's crewed moon landing plan involves building a giant new rocket called Long March 10, which will take off from a new launch pad in Wenchang. The Long March 10 will be capable of sending 27,000 kilograms of payload on a trajectory to the moon, matching the performance of NASA's current SLS rocket and more than tripling China's ability to send payload to the moon compared to their current best Long March 5 rocket, from which the 10 is derived. Andrew Jones reported in May 2023 that China began using a new advanced facility in Tongchuan dedicated to test firing huge rocket engines, including the ones being prototyped and built for the Long March 10. China recently tested firing 3 YF-100K prototype engines in preparation towards making the first stage of Long March 10. For the crewed landing mission at the end of the decade, a Long March 10 rocket will launch a 26,000 kilogram spacecraft named Mengzhao Y, which will carry 3 to 4 astronauts to lunar orbit. There, it would dock with the similarly massive Lanyu lunar lander, itself launched on another Long March 10. After the docking, 2 astronauts will transfer to the lander for a lunar touchdown and return to orbit after exploring the moon for at least 6 hours and possibly a few days. In July 2023, the China Manned Space Agency solicited science payload proposals for the mission's lander. Similar to the instruments NASA will deploy on Artemis 3, CMSA wants these payloads to focus on lunar geology, physics, life sciences, and solar and astronomical observations. On June 11th, the China Manned Space Engineering Office added 10 unidentified astronauts to its Taikonaut Corps, some of whom might fly on China's crewed lunar missions starting at the end of the decade. Similar to ESA's Pangea campaign to train future lunar astronauts in geology and sample collection, which is a highly valuable skill during excursions on the moon, China will provide geology field training to astronaut candidates, followed by activities in mission-specific training simulators akin to Apollo. Through a CASC news release on April 26th, chief designer of China's lunar exploration program Wu Weiren revealed that the upcoming long-term moon base, called the International Lunar Research Station, will have an orbital presence too. While this element of the otherwise surface-based ILRS located on the moon's south pole will only exist circa 2045, the news page says the space station will be of considerable scale and host multiple continuous experiments. CNSA's Chuiqiao satellite constellation should be fully online by then to serve the navigation and communication needs of the many orbital and surface lunar assets operated by China and its currently about 24 partners. China aims to have 50 nation partners and 500 international organizational collaborators for ILRS. Following China's first crewed moon landing, currently targeting 2030, the country will focus on building the surface phase of ILRS by 2035. Key to realizing this is a new super heavy lift and eventually reusable rocket called the Long March 9. China announced in April that it aims to test a Long March 9 by 2032. The rocket can put 50,000 kilograms of spacecraft hardware on a moonward trajectory, which is almost twice the performance of the Long March 10 and NASA's current SLS rocket, both of which will be used to send humans to the moon. Once the Long March 9 is operational, China intends to use it to deliver huge amounts of cargo and possibly even more crew to the ILRS moon base. The rocket will deliver critical infrastructure for sustainable surface hubs via missions named ILRS 1 through 5. This includes infrastructure for energy needs, communications, transportation services, including landers, rovers, hoppers, and ascent vehicles, scientific research equipment, in situ resource utilization technologies, and more. The ILRS moonbase will host large-scale science and technology experiments continually via remotely operated robots and, when available, humans. It was in 2023 that China finalized key scientific goals of ILRS, these goals being learning about our moon's evolution and structure, conducting lunar-based astronomy for doing cosmology and studying habitable exoplanets, observing the Sun and Earth from the scientifically unique vantage point of our moon, conducting lunar-based experiments like studying plant growth. Relatedly, Lingshin reported that by synthesizing data from CNSA's Chang'e 1-4 missions, NASA's LRO and Twin Grail orbiters, and ISRO's Chandrayaan-1 orbiter, China made the highest resolution geological map of our moon yet. The map, which took more than 100 researchers over a decade to compile, is free to use for non-commercial purposes, including lunar geology research and science communications. China itself is using the maps to support its growing lunar ambitions. The team is also working on furthering the map's resolution, including making high-accuracy derived regional maps suitable for advanced mission planning. Building on Chang'e 8 and China's first crewed landing, ILRS will also see multiple demonstrations related to extracting and using local lunar resources, such as water ice and melting soil, to create 3D printed structures. Relatedly, a recent document China submitted to the UN COPUOS concerning the legality of utilizing lunar resources suggests that the country sees such activities as permissible under current international law in much the same way the US-led Artemis Accords does. Some Western experts saw China's action as a positive development since it can now enable, in principle, a mutual dialogue for cooperative resource governance amid a decidedly international fora. In this explainer series, Professor Yun Zhao provides high-level context on China's legal space landscape and the lens through which the country might view such activities. If you enjoyed today's comprehensive moon update, be sure to subscribe to the Moon Monday newsletter by Jatin Mehta, linked down below in the description.
The International Space Station is one of the most complex objects ever created. A machine the size of a football field, built piece by piece in one of the harshest environments imaginable. And we have animated every step. Over 2 decades, using some of the most powerful rockets ever created, we launched hundreds of tons of equipment into orbit. Each truss, module, and power system maneuvered into place by robotic arms, often guided by astronauts' hands suspended in the void while hurtling around Earth at 8 kilometers per second. A one-of-a-kind construction problem. With the inherent vulnerability of life in orbit ever present, simple malfunctions become life-threatening problems. Minor damage caused by space debris can turn into a high-voltage repair mission where one spark can turn an astronaut's oxygen-rich sanctuary into a nightmarish inferno.
And of course, my spacesuit has a Kevlar outer, but there are metal wrist disconnects and other metal parts of my spacesuit that could allow for electricity to conduct into the 100% oxygen environment of my spacesuit, which would be very flammable. That'd be a very bad day for me.
That's Dr. Scott Parazynski, a retired NASA astronaut who is the only person ever to both go to space and summit Mount Everest, flying on 5 space shuttle missions, and has visited the ISS twice. And I spoke to him to get some first-hand stories of what it's like to be strapped to the end of a robotic arm in space, trying to repair a damaged solar panel with spare parts. But the ISS is more than just a satellite. It's a home, it's a workplace, it's one of humanity's greatest achievements. The ISS has hosted life, science, and stories. But after decades of unprecedented international cooperation, its time is coming to an end. Soon, this orbital giant will meet its fate in the upper atmosphere, tearing itself apart in a fiery re-entry, destroying all that hard work in a matter of minutes. Before that final blaze, let's rewind time and dive into the monumental engineering challenge of building this machine. This is the incredible story of the ISS. In late 1998, a Proton rocket cracked the sky over Russia, carrying a strange new object to orbit. It was called Zarya, meaning sunrise. Zarya was no mere satellite. It was a powered spacecraft, a control module, equipped with attitude controls, batteries, fuel, solar panels, and propulsion. A starter engine for a space station not yet born. Just 2 weeks later, the space shuttle Endeavour launched from Florida, its gigantic cargo hold carrying the next module of the ISS, Unity. With the historic moment of the 2 internationally owned spacecraft coming together caught on film. Unity is a short, stubby, 5.4 meter long cylinder without much space for living or experimenting. Instead, Unity acts as a connecting hub. Along its walls, you'll see 4 docking ports, plus 2 more on its ends that in the future will all be used to build up the space station. Here it is in its current configuration on the ISS. But these docking ports could not be directly docked to the orbiting Zarya. Docking 2 spacecraft in orbit has never been simple. Long before the ISS, different systems were tried, each with their own limitations. The early Apollo and Soyuz craft used a probe and drogue, essentially a stick and cone that worked for small capsules but offered only a narrow passageway between vehicles. While fine for crew transfer or modest resupply, it wasn't designed to support the scale and complexity of a permanently crewed station. Later, during the Shuttle Mir program, American and Russian engineers developed the Androgynous Peripheral Attach System. The androgynous name comes from the fact that both the target and the receiving end look identical, with no male or female parts, with the goal of this being a universal docking system, allowing any 2 spacecraft to dock together, as Goddard intended. Each side had a ring with 3 petals equally distributed. One side extended its mating ring with a soft capture, where the 3 petals of each side come together and connect with these latches. At this point, the soft capture ring is retracted and 12 latches engage to form an airtight connection between the 2 spacecraft. The Mir station served as a testing ground for the ISS, and while the ISS was still in its planning stages, a Progress cargo ship slammed into Mir during a manual docking attempt, tearing into one of the station's modules, a stark reminder of how risky orbital dockings could be. Dr. Scott Parazynski was aboard the first mission back to Mir after this collision.
We didn't have the warmest physical welcome to the Mir space station when we arrived during STS-86. There had been this collision to the outside of the Spectre module, so you could actually see, even from quite a ways away, the solar panels on the outside of the space station had these through holes in them, and they were mangled. You could see sort of a divot in one of the radiator panels. This was a pretty beat up space station that we were approaching. On top of that, the orientation of the space station really was ajar. And as our commander, Jim Weatherby, was approaching, and I was supporting him using the camera systems and our computer systems to help make angular corrections to prepare us for docking. It was 6.5 degrees off axis. It was substantially off, really askew. And we weren't sure if there was a problem with our navigation system, with our sensors, or maybe the fact that the space station had been clobbered a few weeks earlier, that there was some other problem going on with the guidance, navigation, and control system of the Mir space station. Ultimately, we found out that the crew aboard the space station Mir had done a star alignment procedure. That's how you kind of coordinate or calibrate your systems. They had essentially chosen the wrong star.
Aboard the shuttle, the crew had to fly in their spacecraft by hand. The androgynous docking system depended entirely on both vehicles being perfectly aligned and flown together with precision. Using laser rangefinders and an onboard calculator, the delicate course corrections began to be made.
The final approach that we had to the Mir space station was very dynamic. Once you're on your approach, you're moving relatively slowly, but in relative space, but you're traveling at 17,500 miles around the planet, and you've got two enormous spacecraft with jet thrusters that you don't want to inadvertently fire and potentially damage a solar panel on the outside of their space station. You don't want to contaminate other parts of the space shuttle. And so there was a lot of hand-wringing, but we followed our training and our procedures. We were able to identify the misalignment between the two spacecraft. And Mike Bloomfield, the pilot on board, input the offsets that I was able to calculate using some grids on our camera systems, and we aligned the two docking systems exactly as they needed to be.
And that was the amazing thing about the space shuttle.
For a successful docking.
Bit by bit,
it was certainly something that we had never experienced before in the Shuttle Mir program, and we were our hearts were racing. Let me just put it that way.
In the background, while these events are playing out, NASA had already started their own design of an American-only station called Freedom. NASA had already chosen a different mechanism to physically connect modules in orbit. They called it the Common Berthing Mechanism. This isn't a docking system, it's a berthing system. That means modules aren't flying in and bumping into the station under their own power. Instead, they're carefully grabbed and maneuvered into place. And it was a big improvement over Mir's old system.
But when you got into the core of the base block of the Mir space station, they had examples of probe and drogue docking systems, which actually required this large probe to be rotated inside the volume of the space station. It took a lot of space. It actually required some kind of interesting gymnastics and fancy flight to get around these probes to get where you wanted to go. So as this International Space Station was being engineered and built around the world, it was decided that it would be really important to be able to transfer very large installations, lab racks included, through hatches. And so we developed the Common Berthing Mechanism, which had a much larger cross-sectional area. It allowed us to essentially transfer things the size of, say, a telephone booth almost, full racks of equipment that would be kind of the cornerstone of the science and the operations of the International Space Station.
Later, in the International Space Station's construction, the Italian-built Leonardo, Raffaello, and Donatello modules used this larger berthing system to deliver tons of cargo to the space station. But the berthing mechanism doesn't come without drawbacks. The electric and fluid connections and bolting sequence take time to perform, so berthing is less ideal for emergency situations or rapid vehicle departure. Crewed missions still rely on the androgynous docking system. This is why Unity went up with two dongles attached to its ends. These are the first two pressure mating adapters that are still docked to the ISS. This side is attached to the androgynous system and the other side to the American berthing mechanism. Their small size and flexibility meant that over the construction of the ISS, they would be moved between nodes and attachment points to open up the possibilities for the space shuttle to dock anywhere. Two modules were now pressurized, but before these modules were launched, one crucial decision had to be made. Where in the sky would the station fly? This decision began with NASA's Space Station Freedom. It was meant to fly solo in a 28-degree orbit, good for launching from Florida, but unreachable from Soviet launch sites in Kazakhstan. After the Cold War, plans shifted. The orbit changed to 51.6 degrees to bring in Russia. That number might seem arbitrary, but it was calculated down to the 10th of a degree. With this large inclination, the station passes more populated areas. The specific 10th of a degree comes because launching from Baikonur at exactly 51.6 degrees, the rocket would barely scratch the border of China. This ensured that no spent booster stages from Russian rockets would ever fall on Chinese soil. The 51.6 degree inclination affects how the station is oriented with comparison to the Sun and Earth, and that would bring some problems when the giant solar panels of the ISS were put in place, but more on that later. In the early 2000s, the International Space Station was still just a shell, 2 modules, quietly orbiting Earth, empty and incomplete. By the end of the year, it will become a home. Exhibition 1 was on the way, and that was about to add a lot more complexity to this operation. How do you turn an empty satellite into a place where people can live and work every day? To keep humans alive in space, the station needed power, control, air, cooling, and livable space, and all of that had to be up and running in less than 12 months. It started with Zvezda, launched in July 2000 atop a Russian Proton rocket, with the Pizza Hut logo plastered on its side to help offset the launch costs. Zvezda automatically docked here behind Zarya. It had an electrolysis system to split water into oxygen and hydrogen. It had carbon dioxide scrubbers, filters to manage humidity, and fans to circulate air that in zero-G would not convect heat. It also carried part of the thermal control system, a liquid polymethyl siloxane loop that helped keep cabin temperatures safe and stable. With the station getting larger, it's nice to have a sense of direction. Like any other vessel, the ISS can be divided into port and starboard, and forward and aft, but in free-flying space, without a horizon as reference, 2 extra directions matter: zenith, pointing away from Earth, and nadir, pointing down toward it. Once the station had a habitable module, the next station was to add systems for control and expanded communications. During STS-92, the shuttle Discovery docked to the forward port of Unity. Using the Canadarm, astronauts removed a non-pressurized truss segment from the payload bay and mounted it on the Unity's zenith port. Because of its position, it became known as the Z1 truss. Since the truss did not fill the entire shuttle bay, the crew also brought up and installed a third pressurized mating adapter on the opposite port, adding another docking point for future assembly missions. The Z1 truss carried the station's first control moment gyroscopes, designed to keep the station stable without burning propellant. But early on, there wasn't enough computing power to rely on them, so control still came from the Russian section. Zvezda came with 2 main engines, each producing 2,300 kilos of thrust, and for precise orientation, the module uses 32 multi-directional attitude-controlled engines, each generating 13.3 kilograms. But every time the thrusters fired, they burned precious fuel that had to be replaced by resupply missions, not a long-term solution. The Z1 truss also carried the first communication systems. The S-band antenna handled voice and telemetry, linking to Earth through NASA's tracking and data relay satellite system. The Ku-band antenna allowed for video and science data to be sent down. The Z1 truss also served as a temporary structure rising above Unity to hold early solar panels and supply power until the main truss system was ready. Exhibition 1 arrived at the ISS aboard Soyuz in late 2000, but the station could only handle basic life support at this point. Its small solar panels couldn't power Unity, so the crew lived mainly in Zvezda and Zarya, relying on Russian systems. A month later, Space Shuttle Endeavour was going to dock to the ISS, bringing supplies and the first of the US-made solar panels. But before the shuttle could dock, one more obstacle had to be cleared. The Progress resupply ship, docked at one of the few available ports, was in the way. There weren't many places where the bulky Space Shuttle could safely attach to in the still small ISS, so Progress had to undock and drift in a temporary orbit, waiting for its turn to return. The first set of large solar panels arrived, rolled up in an unpressurized structural segment called P6. It was installed in a temporary position here atop the ISS. The name itself gives away its final location, P for portside and 6 for its future spot at the very end of the station's sprawling port truss structure. But back then, that part of the structure didn't exist yet, so P6 had to wait, sitting here powering the young station until the rest of its backbone was assembled. Eventually, the relocation of these panels would cause massive problems. To store the power these panels generated, the station used nickel-hydrogen batteries, each holding about 81 amp-hour, to keep everything running during orbital night. But more power also meant more heat. In space, heat doesn't just drift away, it has to be radiated. So, the truss also carried one loop of liquid ammonia to absorb and expel heat, radiating it out into the cold vacuum. In February 2001, during STS-98, the space shuttle docked in this port below Unity. In its payload bay, it carried Destiny, the next US module and the future hub of American science in orbit. Using the shuttle's Canadarm, astronauts rotated the module and attached it here onto Unity's forward port. The pressurized mating adapter, which had been temporarily placed here, was moved to Destiny's forward port. Destiny provided room for experiment racks, control panels, and avionic systems. It also brought a key upgrade, enough onboard computing power to finally activate the control moment gyroscopes. After almost a year, the 95-kilogram gyroscopes were finally spun up to 6,000 revolutions per minute to control the attitude of the station. Each gyroscope gimbals independently, and together their combined angular momentum generates torque that allows the station to rotate. While only 3 gyros are needed, a 4th one is used as a backup. Now, with full control of the station, out of the infinite possible orientations the ISS can travel in, what is the best way to orient the station while orbiting? If the solar panels are tilted like this, facing the direction of travel, the drag increases and tends to pitch the station up. So, 4 gyros are moved together to pitch the ISS down. Some forces are obvious and we can relate to them here on the surface, like the drag on the solar panels, but other forces we don't experience much. Earth's gravity is not uniform, so as the ISS orbits, it can experience a gravitational torque. Modules and trusses stretch out in different directions, and their uneven mass and placement create a constant imbalance. These gyros are constantly adjusted to orient the station in what is called the torque equilibrium attitude. This is essential for tracking the sun, managing thermal loads, aiming the antennas, and lining up visiting spacecraft for docking. The system was a step forward, but not without issues. In June 2002, astronauts reported hearing a growling sound inside Unity. One gyroscope began to vibrate, and hours later, its bearings failed due to overheating. Failures like this is why upkeep of a permanent crewed space station is so hard. NASA had to plan an unexpected spacewalk to physically remove the gyros. Then, a couple of weeks later, the resupply mission had to remove food and supplies to carry 2 extra newly designed gyroscopes that again needed a spacewalk to be replaced. Using gyroscopes does have a limit and can't be used forever. Over time, the external forces build up angular momentum within the gyroscopes. This momentum accumulates until the gyroscopes reach their torque limits, a condition known as saturation. When all 4 gyros are aligned, they can no longer generate enough counteracting torque. To fix this, the station relies on carefully planned burns from thrusters located on the Zvezda service module. These thrusters serve a dual purpose. First, they apply a torque to the station, so that while the thrusters are firing, the gyroscopes can move back to their original positions in a process called desaturation. Second, the same firings are timed and directed to push the station into a slightly higher orbit, counteracting the gradual drop in altitude caused by atmospheric drag. For a couple of minutes, the thrusters increase the station's velocity by 1 to 2 meters per second, and for those few moments, the normally weightless astronauts get to have fun while the ISS accelerates forward.
It's a fraction of a g. It's very, very light acceleration, but it's really neat to be, say, in the middeck of the shuttle, and everything is quiescent, peaceful, and then we perform a slight adjustment of attitude, or a more abrupt maneuver would be the deorbit burn, where actually very gently you get thrown against the walls of the middeck. So you're just kind of slowly pushed back against the wall. So it's a very foreign sort of sensation, especially after you've been in space for a couple of weeks and you're really used to the weightless environment, and then all of a sudden you have just a little bit of a perception of a G-force.
What?
This is what the station looked like at the beginning of 2001. Up to now, the only way to move modules or pressure mating adapters around was using the Canadarm attached to the space shuttle, but that was about to change because STS-100 was about to give the ISS an extra helping hand. The Canadarm 2. This thing was a robotic evolution over its predecessor, and guess who's the astronaut next to Chris Hadfield installing this major new upgrade?
Oh my God.
Scott Parazinski.
But to get it up there
Jeez.
was quite a task because it's a very
That's
large
wild,
robotic
dude.
system. It had to be folded onto itself. And we brought it up in a carrier, and it was basically folded in
Literally,
4
that's
parts. So it was
crazy.
not only the elbow,
Yeah,
but
I
then each
know.
of the arms were
insane,
broken
dude.
as well. So it was kind of bent upon itself. And so there's a lot of coordination between the spacewalkers and those flying the robotic arm inside the space shuttle, and then controllers in Houston and even in Canada as this whole system came to life. So initially this carrier was placed on top of the laboratory module of the ISS, and we had to connect a couple of connectors for power and data to allow it to receive energy, and so we could start to talk to it and warm it up. But then Chris Hadfield and I had to perform 2 spacewalks to essentially unfurl it and allow it to really come to life. So we had several of these, we called them super bolts, but they were massive long bolts that were pinning the quarters of the robotic
no
arm
worries.
down onto
I looked
the
at
carrier
it.
itself.
That's crazy.
So we were able to remove these, put them into what we called a quiver on the side of this carrier, and then we had to unfurl the arm, so basically bring it into its normal arm-like state.
When you say unfurl the Canadarm, do you mean it is powered and you're just like helping it there, or were you physically moving the arm itself without power?
We're mechanically moving it. In fact, I didn't mention it in my description, but yes, we were back driving the joints of the arm. So the arm, although heaters and things were powered, we were not driving the arm. We were actually physically moving it. And so one of the things that was one of the more demanding things I've ever done on a spacewalk was the lift of the booms of the robotic arm. So the 2 shoulder joints have a lot of resting torque, and I had to basically do, I called it the clean and jerk, but I had to physically bring it up, I think about 30 degrees, and that would allow me then to work from a foot restraint mostly, and work on these expandable diameter fastener bolts, giving me access to basically do my job, while Chris would have access from the robotic arm above. So that was one of the critical first steps that actually ended up being a lot harder than we ever imagined in our training.
I'm actually really curious about this because I've never really thought about the types of specific training you'd need to do to prepare to be an astronaut. Of course you need to be fit and maintain your health and everything, but when they're designing the Canadarm, does it only, the motors only need a tiny bit of torque, right? Because of the weightlessness. What sort of strength training do you need to do to lift things in space, I guess? What's the most important thing?
Well, yeah, weightlessness is a bit of a misleading term because you are experiencing mass and inertia. Yep. And so forces can be quite substantial to a spacewalker. So imagine you're moving a 500-pound element, 225 kilos or something like that. That has a lot of inertia. So if you get it going at a certain rate, you're going to have to be very, very careful and deliberate and to react through the center of mass of that object, or you could actually be ripped out of your foot restraint. You could actually go tumbling off as well. So there are substantial forces that the robotic arm has to compensate for. Imagine, receiving, a new module that has to be installed on the outside of the space station. It's got to manage that entire mass, sometimes off of its center of mass as well. So it's quite a complex, high torque kind of activity. So yeah, the spacewalking looks graceful and peaceful, but actually at times it can be very high workload.
In terms of fitness and strength, was there anything that caught you off guard, like some particular muscle that you weren't used to exercising that got exercised a lot in orbit?
No, I think by and large, we've felt very well prepared for the task that we were about to go do. But one of the things that I always championed was pursuit of kind of upper body and including forearm and hand strength. And it's one of the reasons that I recommended and we were able to bring into our astronaut gym a rock climbing wall. So the same types of muscles that are used in rock climbing are those that fatigue the quickest in a really intense spacewalk. So the hand intrinsic muscles and the forearm muscles, you really want to make sure that you're prepared there.
Scott and Chris latched the arm to the ISS here on the Destiny module. If you look closely, sticks and cam knobs are dotted
Destiny
everywhere
knob.
on the ISS. This is where the Canadarm can attach to. Both Canadarms use a system to grab onto satellites that relies on two rings with cables connecting them. As one ring rotates, it moves the cables and creates a self-centering snagging mechanism. But Canadarm2 was not meant to live in one place. Unlike the original Canadarm, which was fixed at one end, Canadarm2 had identical latching and end effectors on both ends, meaning it can move from one grapple fixture to another, increasing the range and flexibility of the ISS for future expansions. The new arm was a major upgrade from its predecessor. With 7 motorized joints, it could bend, rotate, and extend with a carrying capacity of up to 116,000 kilograms. These upgrades made it indispensable for installing truss segments, relocating equipment, capturing visiting spacecraft, and supporting spacewalks with unmatched versatility. But because the arm could move around the station, that meant that each grapple fixture also had to include a way to power the arm. For this, a new design for the grapple fixtures was introduced. 4 electrical connections were placed on the side of the sticks. Once the grapple motion happens, alignment guides ensure the arm connects centrally and securely. Once latched, the arm can draw power, exchange data, and receive commands. Throughout all of these construction projects and spacewalks, the only way in and out of the station was through the space shuttle. That changed soon after one of Scott's missions.
So the flight right after ours was the installation of the joint airlock. And so that became really the kind of the nidus for all of the spacewalks to follow. So the spacewalks that Chris and I did during STS-100 were outside of the shuttle's airlock, which is very capable and it worked just fine. But the problem with that is we had to seal ourselves off from the International Space Station during that period of time. And that basically prevented the rest of my crew members from transferring gear, from doing experiments, working together with our counterparts aboard the ISS. So the combination of our mission was called 6A, the 6th assembly flight, and 7A, the one to follow that installed the joint airlock. That then made it possible for us to do assembly spacewalks outside of the space station airlock, while the rest of our crewmates could be traveling freely between the 2 spacecraft, getting lots more stuff done.
This is what the station looked like when STS-104 was approaching it in 2001. The shuttle arrived here, and in its payload bay, carried the airlock Scott just mentioned. The Canadarm2 slowly rotated the Quest airlock into place and installed it here to the starboard port of Unity. The Quest airlock is split into 2 parts. Here is the larger equipment lock, where astronauts suit up before heading out. Then, they pass through a hatch into the smaller crew lock, seal the door behind them, and slowly vent the air to vacuum. When the outer hatch finally opens, the first thing they see is Earth, filling the view below, silent and impossibly bright. But the growing crew and equipment also required a sturdy structural backbone, and a frame that could carry power, data, and mechanical loads across the station. In April 2002, STS-110 delivered the S0 truss, the central segment that would become the integrated truss structure. To fully utilize this growing spine, the robotic systems also needed to evolve. In June 2002, STS-111 brought up the mobile-based system. This addition allowed Canadarm2 to move along rails spanning the truss structure, no longer confined to a single mounting point. With this newfound mobility, the arm could reach wider areas of the station. Then came the need for cooling and lateral expansion. 2 new truss sections brought with them one of the station's most important lifelines, a complete external ammonia cooling loop. Ammonia was chosen for the station's external cooling loops because it stays liquid in the extreme cold of space and is much lighter than water for the same heat carrying capacity. In each truss, a pump pushes the ammonia through a closed circuit, but its toxicity means it must remain entirely outside the pressurized modules. If a leak ever occurs inside, it's safer and easier to clean water than ammonia. So, the system is designed with an inside water system that carries its heat and exchanges it with the ammonia outside the pressurized sections. As ammonia heats and expands or cools and contracts, nitrogen tanks connected to the storage tanks absorb the volume change by compressing or expanding behind flexible barriers. This keeps the pressure in the loop stable in all operating conditions. For the radiators to work, they have to face the cold of space. Point them at the sun and the whole cooling system becomes useless. That's why the radiator wings need to rotate, constantly adjusting to keep their broad surfaces aimed into the void no matter how the station moves. But that creates a new challenge. How do you keep liquid ammonia flowing through plumbing that also has to spin? The answer is the thermal radiator rotary joint. Inside, flexible hose couplers let ammonia flow through rotating lines. Power and data cables pass along the joint through a transfer assembly, while motors and gears control the swing itself. Altogether, the joint allows each radiator wing to sweep back and forth 210 degrees. Between 1998, when Unity joined Zarya, and 2003, 14 shuttle missions assembled 4 main pressurized modules, along with vital truss and airlock components. Some of these pieces were launched separately and connected for the first time in orbit by nations that were fighting a Cold War less than a decade before. Construction wasn't flawless. Destiny's cables were miswired, Quest developed small leaks, and Canadarm2 lost a motor soon after activation. But those setbacks were minor compared to what came next. A small piece of foam would halt assembly and reshape spaceflight. This is the story of the ISS that we will cover in the next episode of Real Engineering that you can watch early on Nebula, and there's never been a better time. In 2003, the ISS hit a sudden and catastrophic halt in its decade-long construction process. The Space Shuttle Columbia disaster sent shockwaves through the space launch industry. The Space Shuttle was the only vehicle capable of hauling the massive building blocks of the ISS into orbit. With a cavernous 18-meter cargo bay and powerful engines, it could carry entire station modules weighing more than 20 tons at a time. The station's assembly froze mid-construction. Its growth paused in silence above the Earth for 2.5 years. Without Russia and the Soyuz, the ISS would have been lost. Thankfully, that did not come to pass, and the Space Shuttle would soon return to orbit, with some new improvements. This is how the ISS defied catastrophe and how a fractured alliance of nations and a grounded fleet still managed to keep humanity's most remote outpost alive. This is the insane engineering of the ISS. Part 2. While engineers on the ground were scrambling, looking for clues to try to find the culprit of the Columbia disaster, NASA had to look up to the skies as well. The ISS was not meant to fly uncrewed. The 3 astronauts on the ISS had to wait 2 months before the next Soyuz arrived to rotate the team. 3 returned home, 2 stayed behind to keep the station alive, the safest minimum crew size. Now it was time for the ISS to go into power-saving mode. Experiments were cut, and the lonely crew kept the station running for as long as possible. With the cargo capacity decimated, water and food were prioritized. These were the station's lifeline, the Russian Progress resupply ships. The day after Columbia, one launched with food, water, and essentials. 2 months later, the next cargo ship would arrive. Normally, once a new Progress arrived, the old one would be released and sent back to burn up in Earth's atmosphere. This time, instead of discarding the previous Progress ship, they kept it docked. Every bit of extra space could be used for food, water, and spare parts, critical for the station's survival plan. Parallel to figuring out how astronauts were going to live aboard the ship, it was imperative to get the shuttle back in operation and safely. On the ground, they ramped up launch monitoring. NASA deployed high-speed tracking cameras around the launch pad, and they installed onboard sensors to detect foam impacts in real time. During the very first mission after Columbia, STS-114, 16 pieces of foam came off the external tank during launch. One of them was quite large, around 91 by 30 centimeters. Before Columbia, there was no way of knowing how much foam impacts affected the heat shield. So, a new system was set up to inspect the thermal protection system of the shuttle once it was in orbit. This is the Orbiter Boom Sensor System. It is a long 15-meter boom that could be attached to the shuttle's canadarm, outfitted with lasers and high-resolution cameras. The idea was to let astronauts scan the shuttle's heat shield tiles and reinforce carbon-carbon panels on the wings and nose cap. This is footage from the boom sensor aboard the first shuttle flight after Columbia. Discovery also performed the very first rendezvous pitch maneuver before docking with the ISS. Essentially a backflip that allowed the ISS to take numerous photos of the underside to inspect for damage.
No.
That same mission included 3 spacewalks. One
7
to
minutes
replace
is
the
all
old
I try to play
gyroscope,
with you.
and the other 2 being newly developed safety procedures. Dangling from the end of the Canadarm2, an astronaut was tasked with inspecting the space shuttle, and they actually physically removed 2 gap fillers that had started to protrude from Discovery's underside. Had those fillers remained, they could have created dangerous
What is
hotspots
this?
during re-entry.
What is this? Hold on.
The next spacewalk was designed to
Oh, these
test
people are
new
trolling in the
on-orbit
other server. I'll be
repair
back.
techniques. Samples of heat shields with simulated damage were stored inside Discovery's payload bay. Spacewalkers were tasked with injecting sticky sealant into the cracks using hand tools. Shallow scratches were filled with a liquid wash that soaked in and restored heat resistance, while deeper gouges were filled with a thick paste that hardened in orbit. All these samples were returned to Earth to confirm their effectiveness. The spacewalks proved that even if the shuttle was damaged, astronauts could inspect and repair the heat shield in space. By September 2006, the shuttle was finally cleared to restart building the ISS, and it was in desperate need of more power. The portside solar panels came up first. Half of the P6 panels were retracted to make the station symmetric and to avoid collisions as the new solar panels span around. Next came the starboard side. The solar arrays on the ISS are stored in folded blankets inside rectangular boxes mounted on the truss. Each wing consists of 2 blankets of solar cells attached to a central mast. A motor drives the mast outwards, and as the mast extends, it pulls the folded solar cell blankets out with it. Guide wires run through reinforced holes along the blanket to keep the structure aligned and under tension. Each truss also carries its own ammonia cooling loop and radiators to keep the panels from overheating. Then came STS-120 in October 2007, a mission carrying the second node of the system, Harmony. Harmony was initially attached here to the starboard side of Unity, so it would be out of the way while the P6 solar array was relocated. Canadarm2 reached out and grabbed the truss segment here, just above the station, but it couldn't carry it all the way to the far end of the ISS, so the arm passed it to the shuttle's Canadarm. From there, Canadarm2 moved along the mobile base system to the station's edge, took the truss back, and guided it into alignment. Then, 2 astronauts stepped outside to bolt it into place. One of them was Dr. Scott Parazinski.
We'd been out at the very tip of the space station. We had, working with Dan Taney and Stephanie Wilson, who were driving the robotic arm. We were able to bring the P6 truss in close proximity to the P5 truss, and we were able to bolt the thing together. We mated the electrical connectors. We thought that the most challenging part of the mission had been accomplished. We were starting to celebrate, but we were wrong. This is when it really got exciting. So as we got out of our spacesuits and floated into the laboratory module, we saw everyone hunkered around this small CCTV monitor, trying to see what was going on. And we couldn't really see the details, but it looked like there had been a rip in the solar panel. And this was at a position where the solar panel was only partway deployed, and we couldn't retract it at this point. We couldn't extend it.
This is what the situation looked like. One of the solar panels did extend, but the other side only extended 80% of the way. From the window of the ISS, they could see a small hole in the solar panels, but they couldn't really tell what had happened. The first obstacle was distance. The torn array was located far from the normal reach of the Canadarm2. The only option was to attach an astronaut to the long boom used to inspect the bottom of the shuttle, and this carried a lot of risk. First off, solar panels in space don't need to hold their own weight, so unlike panels here on Earth, the panels on the ISS are a lot wobblier than you might imagine.
Yeah, these aren't your mom's and dad's solar panels that we have aboard the ISS. They're quite unique. They are mounted on thin film, so they're basically circuit boards that are hinged, sort of like leveler blinds that you might have at home. But they're very, very flexible. And in fact, if you were to push on the solar panel in its partially deployed state, it would float away from you very gracefully like a sail, but then ultimately it would work its way back. And in fact, that was one of the major concerns that they had for sending a spacewalker out there, because this solar panel was likely damaged. And so there were concerns that there could be arcing of electricity, high voltage, high current, from the solar panel into my spacesuit. And of course, my spacesuit has a Kevlar outer, but there are metal wrist disconnects and other metal parts of my spacesuit that could allow for electricity to conduct into the 100% oxygen environment of my spacesuit, which would be very flammable. It'd be a very bad day for me. So engineers very graciously.
Flammability of that 100% oxygen environment in the spacesuit. You remember how that played out in For All Mankind on the moon with the Russians, Aurora, when they shot that one Russian and then the inside of his spacesuit lit up on fire, got burnt to the crisp.
Thought about my safety, so we ended up wrapping the metal parts of our spacesuits for both Doug and myself with Kapton
Y'all just need to watch it.
Yep.
tape so that there would be no risk of conductance of electricity into our spacesuits. And then we weren't able to have any direct contact with the solar panel. So I actually had I've got one over here, I think. Yeah. So this is kind of interesting. This is a hockey stick, very similar to what I used in space. So this is not the real one, but it's made of the same materials. It's got a tether loop on the tail of it. But I would use this tool, stick in front of me such that the solar panel would pass harmlessly above my head and beneath my feet.
From the images,
Paşa bir öpücük ver. Paşa bir
Fucking hilarious.
from talking to the astronauts, the team on the ground had already figured out the problem and a potential solution. The guide wire running along the solar panels had been damaged, so Scott needed to get out there, cut the guide wire, and reconnect them with a MacGyvered repair using materials available on the ISS.
And then I have here, actually, one of the engineered cufflinks that was used on 1G mock-ups of the solar panel here in Houston. So this is actually what it looked like. This is one of the shorter ones, when we had a couple of much longer ones as well that I installed. This allowed me to poke this through a hole in the solar panel on one side of the damage, and then this one ended up going on the other side, and then the load path could be absorbed by this piece of wire. But the cool thing, the really cool thing, and this is one of my prized possessions, this was given to me by the engineer who invented this repair. And this is actually 2 pieces of cardboard from a Domino's pizza box. They were working around the clock. They worked for like 72 hours straight. But this engineer had this idea for these cufflinks, and he cut a Domino's pizza box, tied it together with a couple of pieces of string, and he threw it on the table and said, "Here, what do you think about this?" And that became the solution to save the solar panel.
That's crazy. I guess my question is, like, do the people on the ground have like a full inventory list of what's up on the ISS? Like, how do they know what you can actually build?
Yeah. Well, they knew exactly that we had this 12 gauge wire aboard the space station. This is aluminum shim stock that's been covered in tape so it wouldn't conduct. This is a threaded fastener that we had in stores. So they know exactly what we had aboard the space shuttle and space station inventory. And that became, the shopping list. You need to go to such and such a location aboard the space station and get out the reel of 12 gauge wire. And then they created a procedure around that to allow for the assembly of these things. And they had to be measured incredibly precisely. So this couldn't be too thick, or it wouldn't go through the solar panel. It couldn't be too long, or it wouldn't pass through. The length of it had to be measured exactly to spec.
So, with the cufflinks made and Scott's wrist wrapped in insulating tape, it was time for the mission. He left the ISS through the Quest airlock and spacewalked his way to the edge of the ISS. Here is where he would be picked up.
Yeah, so I was picked up, on the truss of the International Space Station using this, as you mentioned, the Canadarm2 and the orbiter boom sensing system inspection boom. And then I had a 45-minute commute, and it was a wild ride because it's a very ungainly robotic arm system that was at risk of hitting other solar panels, hitting the other parts of the space station, and of course they didn't want me to get anywhere close to the proximal solar panels that we had to kind of work around. So it was a very complex maneuver that Stephanie had to fly me on. And I remember vividly, we were all together. This is a day before the spacewalk, hunkered together in the joint airlock. My crew with Pam and Paolo, Stephanie, and Dan, and George, and Doug, as well as the ISS crew. And they had created this animation of this extraordinary long arc and how the whole arm was going to be reoriented. If a pin could drop in space, you would have heard it. It was there was just, all of our jaws were dropped. We couldn't believe that we were about to go do something as wild as this. But miraculously, the plan that they came up with was a home run.
From his helmet camera, you can see the mission unfold. Once he got into position, he got straight to work. He cut the guide wire and started to sew in the cufflinks. One by one, Scott installed 5 cufflinks into the solar panel in a tense 7-hour mission outside the station. But it worked. The array extended fully, restored to full functionality. This repair remains one of the most complex spacewalks ever performed. And to this day, the solar panel on P6 has those cufflinks Scott installed.
So did we ever actually figure out what caused the damage to the guide wire in the first place?
I can't find it right now, but they actually gave it to me. It was really, really cool. After I cut out the piece of frayed guide wire, we have a trash can. It's just a tiny little pouch. So I was able to store that, bring it back inside, and ultimately back to Earth. It was sent to a laboratory, and they did analyses on it and determined that there was a tungsten, which is clearly a man-made object, had come in contact with this steel braid cable and had clipped probably 2 of 7 steel braids, steel strands. So it's amazing you can actually do that kind of sophisticated analysis on a tiny little piece of steel braid cable. But it was clearly as a result of a man-made object striking this guide wire in a unique way.
This is what makes building in space so unforgiving. All it takes is a fragment, a tiny shard from an old satellite, racing around the Earth at thousands of kilometers an hour. By pure chance, it struck the ISS. The damage was small, but the risk was enormous. After this successful repair, Harmony was relocated to the forward end of the Destiny lab. The pressurized mating adapter 2 was then reattached to Harmony's front end to serve as the new shuttle docking port.
So what would have happened if you didn't fix the solar panels?
Yeah, there's a lot of conjecture there, and I don't know what mission managers would have ultimately decided, but there was talk of us having to go out and jettison the solar panel. That was the next thing that we would have had to have done to make it safe for us to undock. The concern was, there's quite a bit of momentum exerted when the shuttle undocks, and then there are jet thrusters that are fired, and those might have somehow interacted with the limp noodle solar panel out there and ripped it apart. So it's likely that we would have gone out on another spacewalk, thrown it away, and on a subsequent flight probably launched another solar panel, for the main reason that the space station program was really critical to the power generation of that solar panel. There are European and Japanese modules that were just about to be launched. It wouldn't have really been possible to support them without that additional power.
Europe and Japan wanted their own facilities where their astronauts could run experiments, test new technologies, and bring home results for their own space agencies. STS-122 in February 2008 brought the answer: the European Columbus Laboratory. Carried into orbit aboard Atlantis, Columbus was attached here to the starboard side of Harmony. 2 spacewalks connected it fully. With this single module, Europe gained a permanent orbital research hub. But scientific research wasn't Europe's goal alone. Japan had its own ambitions and its own module, Kibo. The core pressurized module of the Kibo complex arrived in May 2008 on STS-124. It is the largest module on the ISS and is installed on the port side of Harmony. Earlier flights had already delivered the logistics module and the Japanese robotic arm. With this final piece, and after several spacewalks and robotic operations, Japan's vision of a complete research facility in orbit became real. With the science labs needing extra power, it was finally time to bring up the last of the large solar panels, bringing the station to full power by March 2009. But the solar panels on the ISS are not fixed in one position. The station orbits Earth every 90 minutes, and its angle to the Sun changes constantly. Huge rotary joints rotate entire truss segments, making a full turn every orbit to keep the panels facing the Sun. The Sun's angle also changes as Earth orbits around the Sun. Beta gimbal joints make vertical adjustments like this. The daily adjustment is about 4 degrees, but over a year, the panels can move up to 70 degrees. This is where the 51-degree orbit began to cause problems. The panels were designed for the US-only Freedom Station with a 28-degree orbit, where every pass took it regularly into Earth's shadow. But the 51-degree orbit of the ISS means at certain times of year, the station stays in constant sunlight for long stretches. In those periods, the low angle of the Sun causes one set of arrays to cast shadows on the others, cutting power. Even worse, parts of the same array can be in shadow, while other sections and their supporting beams take the full heat of the Sun. These beams that give structure to the wobbly solar panels are vulnerable. Even 20 minutes of uneven shadowing can make sections heat and expand at different rates, twisting the mass and risking damage to the entire array. Solar panel arrangement is an optimization problem. While NASA came up with their solution, they opened up a $30,000 prize to whoever could create a program that would optimize the solar panel's position while preventing problematic shadowing. This is what they came up with: a smooth turn of solar panels with slight delays to avoid these shadows. This is what the station looked like by July 2009. The station had come a long way, but more was coming up. One key capability was still missing: exposure to open space. In July 2009, STS-127 delivered Kibo's Expose facility, installed using both the Japanese arm and Canadarm2. Mounted outside the Kibo module, it finally let researchers expose materials, equipment, and living organisms directly to the vacuum of space. As operations grew more complex and long-term stays became routine, astronauts needed better life support and living quarters. STS-130 answered that call in February 2010 with the delivery of Tranquility. It was mounted to the port side of Unity. Tranquility brought new air revitalization, water recycling, and exercise equipment, but it also came with something else, just for fun: the cupola, an incredible panoramic viewing module that made life on board the ISS much more enjoyable. But installation didn't always go smoothly. Initially, the cupola was attached to Tranquility like this, not in its final location. Once in space, the plan was for astronauts to attach a thermal cover over the cupola and position it here. But astronauts were having a hard time placing the thermal cover. The tolerances were much tighter than expected. Bolts weren't included in the 3D models of the cupola to save memory on the file, which meant the digital mock-ups didn't show how little room actually existed for installation. To make it worse, the team realized that the cupola had been the only module mated with another module on Earth, so the extra gravity made the bolts even tighter than expected. which caused several bolts of the common berthing system to jam during relocation. This led to tense last-minute calculations and meetings to ensure the cupola would fit without structural damage. With all of those setbacks out of the way, the cupola was finally moved to its final location here on the Nadir Port of Tranquility. The cupola's 7 windows give astronauts an incredible view while keeping them safe from the harsh environment outside. Each window is composed of an inner scratch pane, 2 thick pressurized panes, and on the outside a debris pane shield. When not in use, the windows are protected by manually operated shutters that the crew open and close with a simple hand crank. This is a mechanical connection. The shaft that turns the shutters runs straight through to the vacuum of space. Only 2 O-rings stand between the interior atmosphere and the void outside. Then came STS-135, the final space shuttle mission. It brought up the Raffaello module, packed with spare parts, tools, and supplies to sustain the station in a post-shuttle world. After the shuttle's retirement, expansion continued through Russia's launch services. In July 2012, they launched the Mini Research Module 1, Rasvet. Attached to the Nadir port of the Zarya module, it provided cargo storage and internal workspace. But relying on Russia was not in the United States' best interest. This was the beginning of a new era. The commercial space launch industry was about to rapidly expand. In January 2014, the Cygnus CRS-1 mission delivered a large batch of supplies and experiments aboard an orbital sciences vehicle. Around the same time, SpaceX Dragon missions also became a regular part of ISS resupply and hardware delivery. By 2015, the station had become fully operational. It had multiple research labs, robotic systems, observation windows, and docking ports. This technically marked the end of the original construction phase for the ISS, but more was coming. The old shuttle-era androgynous docking system had done its job for decades, but it was big, heavy, and designed only for the space shuttle. With new commercial spacecraft on the horizon, NASA needed something universal. That change came with the International Docking Adapter. It uses a modern androgynous system, but instead of a mechanical slam, the adapter uses a soft capture system. As a spacecraft approaches, guidance sensors and small alignment petals gently draw it in. Once contact is made, active latches close slowly and pull the vehicles together for a tight, hard seal. The process is fully automated, far smoother, and safer for both vehicles. Technically, the adapter is smaller. The docking tunnel is 0.8 meters wide, but the adapter's overall mass and complexity are much lower. It's also equipped for power, data, and fluid transfer between vehicles, something the old androgynous shuttle system couldn't do directly. The first adapter was launched in 2015 aboard a SpaceX Dragon capsule, but never made it, lost in a launch failure just minutes after liftoff. A year later, the second adapter reached orbit, packed inside the unpressurized trunk of a SpaceX Dragon. Once at the station, the Canadarm2 pulled it out and carefully positioned it on the front end of pressurized mating adapter 2 attached to the Harmony module. The third built adapter arrived in 2019 aboard another Dragon. Together, the 2 ports, one facing forward and one facing zenith, now serve as the main gateways for Crew Dragon and Boeing Starliner. For the first time since the shuttle era, America had a way to bring its astronauts to the station on its own vehicles, using a docking system designed for the future. It was now time to start experimenting with new ideas. Back in the 1960s, NASA had explored inflatable living spaces under a project called TransHab, meant for deep space missions. When the program ended, Bigelow Aerospace acquired the NASA patents and revived the concept, developing it into a commercial line of expandable space modules. Launched on April 8, 2016, the Bigelow Expandable Activity Module, or BEAM, rode to orbit folded inside the Dragon's capsule's trunk. Once docked, the Canadarm2 reached in, pulled the compact cylinder free, and attached it to the aft port of Tranquility. At first, BEAM was only 2 meters long and 2.5 meters wide, a small folded package. Once expanded, it grew to about 4 meters in length and 3 meters in diameter. Unlike the rest of the station's metal modules, BEAM was made of layers of fabric, Vectrin, Kevlar, and other high-strength materials designed to protect against radiation, micrometeorites, and temperature swings. Inside, a flexible bladder held air and gave the module its shape once inflated. What was meant to be a 2-year test kept going, and today, BEAM is still attached to the ISS, used for storage and data collection. More importantly, it proved that soft-sided habitats could work, paving the way for future space stations, lunar bases, and missions beyond Earth orbit.
As an engineer, the battle between Windows and macOS isn't always just an issue of preference, it's an issue of productivity. Most engineers use Windows, and that's because there are countless engineering programs that just don't have a Mac OS build. SolidWorks, one of the most popular design softwares, is Windows only. I much video on Bean, you could within 5 seconds. It sees keyboard and mouse, and there is a software and Dragon operating system. And all of this happens on your local network. Nothing.
Not supposed to do video. Yeah. Wow.
Would you look at that, man?
Wow, what's the shadow behind it? It's different.
Wow.
It's wild.
Dude.
Yeah.
No way.
I mean, to be fair, I would want that on my phone.
Fiend.
It's gone. It's gone. Oh my God.
That's LOS, loss of signal.
And liftoff of Artemis 1.
Artemis 1 was incredible. It was an iconic mission.
I was able to watch the launch of Artemis 1, and I'll never forget, I just turned into a small child, and I just was screaming at the rocket for about 30 seconds.
That is our generation, the Artemis generation, that defines the starting point of our exploration future.
Next thing is getting ready to fly the crew on Artemis 2.
This mission paves the way for sustained missions on the moon and then Mars.
We've got spaceflight vehicles that are down at the Kennedy Space Center that are being built and integrated. We've got components of a rocket that are being assembled.
We have international partners. We have commercial partners and industry partners.
We've got the designs ready to go, how we're building up the operations.
It's real. The team is ready to go.
4 names, 4 explorers, answering the call to once more rocket away from Earth and chart a course around the moon.
This is the mission of Artemis 2.
Never before had man traveled so far, so fast, or looked so closely upon another celestial body.
It's one small step for man, one giant leap for mankind.
Apollo was so amazing because we didn't know we could do it. The Apollo generation showed what was possible.
For me personally, I think it's an important endeavor to return to the moon. And as we look towards Mars, the moon is going to be an important staging area for us to learn quite a bit. The longest we were ever on the moon as humans was 72 hours. We have a lot to learn yet.
And as we leave the moon in Taurus Literal, we leave as we came, and God willing, as we shall return, with peace and in hope for all mankind.
The Artemis campaign is really a set of test flights. We haven't been to the moon in over 50 years, and so there's a lot of new systems that we need to test out. We're going to a new part of the moon, the South Pole, that we've never been to before with crew. The Artemis 2 mission is going to take the next step in our flight test campaign. We're going to focus on what are the new systems that we need to test out so that we can fly crew to the moon and safely bring them back home. That really sets us up for our big goal, which is the return of human crew to the surface of the moon.
It's so important what we learn in that mission to the moon because it instructs us on how we're going to get to Mars. This is a generation-defining effort.
My name's Jeff Radigan. I'm the lead flight director for Artemis 2. Here in Mission Control, I direct the operations of the spacecraft and communicate with the crew on board in order to have a successful mission of a first mission back to lunar space in over 50 years. We want to get back out to lunar space. We want to fly around the moon. And so to be a part of that is just very meaningful to me. It's something I get excited about when I wake up in the morning. It really is the next step in space exploration.
GC, go. Guidance, go. FIDO, go. Prop, go. GNC, go. Max.
This room has a lot of historical significance. We originally flew the space shuttle out of here, and we're looking forward to flying Artemis 2 out of this room here in the not too distant future.
Once the vehicle clears the tower, control of the spacecraft is handed over to Mission Control Houston. At that point, the team in Mission Control, led by the Ascent Flight Director, will take over. It's a very distributed team. Think of it as a big pyramid. At the top of it sits the flight director, but around him are specialists in every system on Orion. They'll have teams in the front room that are working with the flight director. They'll have teams in the back room that are supporting the front room operators to make sure that they're specialists in all of their systems, just in case we have a problem that we haven't seen. And by the way, in my 20 years of human spaceflight experience, I guarantee you we're going to have a problem that we haven't seen.
Oof.
My name is Natasha Peak.
The toilet.
I'm a flight dynamics officer for Artemis 2.
But it was Daniel's
We
fault.
are trajectory specialists when it comes to Orion. Really, my job is to know where your spaceship is and where it's going. And if we need to come home for some reason, come home early, or we get off track, our job is to figure out how to do that. This mission is fundamentally different from a mission you might do in low Earth orbit in a lot of ways. But one of them is that we're looking to rendezvous with the moon. Every minute you wait to launch, the moon is moving. So in order to rendezvous with it efficiently, we have to change the inclination of our orbit to make sure we line up with the moon. In a month, you get about 14 days of a launch period. Our team all hunkers down, and for every day, we look at the open and close of the window and come up with a trajectory end to end, from liftoff all the way through splashdown.
You know, I often talk about that launch ops is like a team sport. It's certainly you have to produce on game day, but that the preparation for a championship begins in the off season. We've made some significant upgrades since Artemis 1, and that includes not just the software that you see out here running on the consoles, but it's also in our model and simulation environment. The big difference between Artemis 1 and Artemis 2 is, of course, the crew. And it's the systems, the new systems that are specifically in place to support a crewed flight. And so we have new launch commit criteria, we have changes to our procedures, changes to our timelines, and we want to make sure that we've gone through those time and time again so that when launch day rolls around, we're ready for anything that the hardware may throw at us.
We woke up this morning, went through medical checks, had breakfast as a crew while Charlie and her team were getting the simulated vehicle ready for launch day. We got in our crew transfer vehicles, our CTVs, we came out to the pad. We went up 2 elevators to the 274-foot level, and we met there, our White Room closeout team. So it was a great end-to-end run-through of what we will do when we get on this vehicle and head to the moon.
There are no shortcuts. I mean, you have to do it all because on launch day, that is game day. And it is in all of our work together that gets us to a successful T0 and a safe and successful mission.
Hey, Sam. What's going on? Not much. Long time no see.
Damn.
Let's see.
The seriousness of what it takes to take the risk with humans in and of itself creates enough of a pressure for the entire organization, enough of a concern, enough of a sense of rigor. Everything goes up a notch.
We have to have an atmosphere to breathe, a temperature to be able to control, to be able to take out the carbon dioxide and the humidity that's in the air, feed the crew, deal with a small environment, proving that we can fly by the moon and come back and have a safe reentry.
There's an extra element when you have humans on board, the nuances by which the system operates, the understanding of what it is to live in this crew module that we have. Artemis 2 is also another flight test of the other systems that are required to enable human space exploration. That is life support system, that is displays, that is the controllers, the stick that you need to fly a spacecraft. All those pieces were not part of Artemis 1, but are really key for Artemis 2, and the crew will need that capability to go forward to do human space exploration.
When you go to the moon, you're 250,000 miles away, and there's no choice. It takes time to get home. Everything we check, everything we try and make sure we understand, we double, we triple, we quadruple check, because we want to make sure we get it right.
The mission will prove the Orion spacecraft is ready to keep astronauts alive in deep space and allow the crew and ground teams to practice operations essential to the success of future missions.
This top portion is the crew module. It's the pressurized area where the crew sits. The bottom portion here with the solar arrays and the engines, primary engines, is what's called the service module.
The European Service Module, or ESM, will provide electricity, water and air to NASA's Orion crew capsule, as well as maintaining temperature for life support.
It's been a fabulous partnership with our ESA partners. The agency made a decision a long time ago that we want to do lunar exploration as a global partnership.
Now that we're having crew, that's the new element for Artemis 2 and onwards. We will really go into the testing of the life support systems and try to figure out how is that behaving with the astronaut in the loop, how is the CO2 scrubbing working on the crew module side, how are we providing the oxygen to the astronauts and the water.
That environmental control system is so complicated. It's a series of chemical and mechanical and electrical engineering problems that all have to come together. That spacecraft has to basically be a mini Earth. And that Earth is basically driven by the elements of that life support system.
We also have crew interfaces with the crew piloting the vehicle. Artemis 1 was uncrewed, and so we're going to go do a checkout right at the beginning of the mission while we're in an Earth orbit to be able to ensure that the crew is able to successfully pilot the vehicle.
We're not just testing the systems in Orion. One of the key things we really want to do is we're going to do science.
When we think about Artemis 2 science, there are really three big areas that we're studying. One is understanding the space environment. The second is understanding how that environment interacts with life and humans and the systems. And then the third is looking at the moon itself from a vantage point where humans haven't looked for over 50 years.
They're going to be describing what they see. They'll see things that human beings have never seen before. They'll be describing, observing, and documenting what they see for the scientists back home.
They've done a significant amount of training in the field here on Earth, learning about geology and planetary scale processes. They'll be looking for the evidence of those processes from orbit and describing to us anything unique that we maybe haven't been able to really sense with orbiters and robotic measurements.
We're also going to do human research on the crew members themselves. We haven't had data sets for over 50 years on how the physiology of the crew themselves adapt to the radiation environment, to the microgravity environment so far away from Earth.
When you think about Artemis 2, we've never had humans get on top of an SLS rocket. And when that rocket launches, 8.8 million pounds of thrust are going to defeat gravity for a 5.8 million pound vehicle. So they're going to feel vibrations and hear sounds that no humans have ever experienced.
If you want to be an astronaut, that's the thing you've been waiting for your whole life. Riding the elevator up the rocket, climbing in that capsule, very surreal. I often say that the only reason anybody actually gets on a rocket is because it'd be too embarrassing to turn around and run away from the rocket. Once the fire starts coming and the rocket starts vibrating and you lift off, it's a completely different experience.
When you put crew on a rocket, it's no longer a test flight. This one needs to perform and will perform as good or better than the first one did. No doubt about it.
Artemis 2 begins with launch
We're
from
gonna
Kennedy Space
lose
Center.
to China.
Getting them through that 8.5 minutes to get them to escape Earth will be the first big milestone.
First, you'll do about 2 minutes of flight with the boosters. The boosters will separate, leaving you on just the core stage all the way through about 8 minutes into the mission. At that point, the
may
upper
not be
stage
ready
will
till
separate
2031
from
if
the
the
core
company
stage
experiences
and
delayed
perform a
typical
perigee
passive
raise maneuver to keep you in a stable orbit. The crew's going to be in a high Earth orbit, checkout orbit. So this is a highly elliptical orbit that just takes them up away from the Earth and then back down close to it. From there, Orion backs away and separates from ICPS, preparing us for manual piloting by the crew of the Orion vehicle, imagining that they are approaching and docking with the upper stage of the rocket.
The crew will have their hands on flying it for the first time, and that allow them to see, do we have the pulse size correct? Do we need to make the pulse size smaller? Do we have enough thrust? Does it have enough control authority to give us the rates and the movement that we need to in the vehicle when we need it?
We need to really understand how Orion's going to perform in order such that we can dock it on future missions. We're going to fly information for a good 2 hours to ensure that we can do the checkouts to really understand the way this vehicle is going to operate. As we do ascent and as we go through our Prox Ops demo, it's going to be a long day for the crew, it's going to be a long day for us on the ground.
Once we convince ourselves that the systems are solid, we will engage the Orion main engine, and that will commit us to what we call translunar injection.
The translunar injection burn is the big burn that puts us on the path to the moon. For that flyby out to the moon, we're doing what we call a free return trajectory. The idea there is that without doing any more major burns, you can just coast, and the gravity of the moon will redirect Orion and bring it back to Earth safely.
Hey, Apollo 13, Houston, you have a go for...
We have done a free return only one time, and that was during Apollo 13. We have designed deliberately to do a free return on this particular mission because, again, our risk tolerance, our willingness to take risks with the vehicle, with the crew on board is much, much lower for a crewed test flight.
The next 3 days are spent in transit, and so the crew has activities to, again, continue to check out the systems on the Orion that we weren't able to get to in the first day. We need to go through checking out the radiation shelter, that all of our stowage is in the right spot. We need to check out the cabin to ensure that we can depress it to be able to dock within HLS in the future. Then we're going to fly around the moon.
You'll fly by the moon at about flight day 5. You'll be
Well,
between 2,900
apparently,
and
as of April
7,900 nautical
15th,
miles from the lunar surface.
Axiom says they're
That'll be the
nearly
first time
finished
we'll
with the
have
critical
4
design
crew
review
members
and intend
being
to
able
test
to
the
share
suits
the
in
experience
space
of
as
seeing the
early
far
as
side of the
next
moon
year.
together. They'll be the most separated from Earth than any 4 humans could possibly be at that point.
We're going to turn the spacecraft so that you can have the best view of anybody of the moon in 50 years. We want to ensure that we're getting the videos of the moon that all of us back here on Earth want to see, and ensuring that all of our systems work on the far side of the moon as well, the way we expect. Once the crew flies past the moon, they'll begin the 3-day journey home, where they'll again begin to do some checkouts, including trying to take the cabin down to a lower pressure, which is needed for future flights. Finally, as they get closer to Earth, they're going to prepare for re-entry. We have to configure the cockpit, do our final targeting, final burns, get the crew in their suits, get them in their seats, and then they'll get into the re-entry sequence.
The back half of the crew module has the heat shield, which is covered right up until just before what we call entry interface, when you're re-entering the atmosphere, at which point the crew module separates from the service module, puts the heat shield towards the Earth, and then begins its entry.
The way Orion enters the Earth's atmosphere, it's a capsule shape, and when that capsule engages with the atmosphere, it hits at a tremendous speed. The speeds that we're enduring produce temperatures as hot as 5,000 degrees Fahrenheit, which is close to the surface of the sun. The way we protect and absorb that energy is we build a heat shield. That heat shield serves as a function to transfer it and absorb that energy so that, ultimately we can come down gently on our chutes.
That 19-ish minutes is the most critical of a flight. That heat shield has to work.
But
the guidance has to put them in
what
the
would
right spot.
SpaceX do?
And if we're
SpaceX doesn't
anywhere
have a
close to
lunar
where
suit.
Artemis 1, we're going to drop that capsule within a couple miles of the landing ship.
Splashdown.
We're going to land off the coast of San Diego in the Pacific Ocean, and we're going to test out in real space in real time the recovery of crew from the capsule. So all of these are new things that we haven't had to do before in a long time.
They'll be recovered by our recovery forces, and we'll see their smiling faces. That's the mission. That's Artemis 2.
We learned a ton on Artemis 1. A lot of just how the vehicle works and how to fly it, especially from our perspective.
When SLS cleared the tower at Pad B, we put Orion exactly where it needed to be. The upper stage conducted a perfect burn. Orion spent an incredible retrograde orbit around the moon, achieving a distance further than any spacecraft designed to carry humans had ever been. And when it came back to Earth, it performed the first ever skip re-entry of a vehicle.
For Artemis 1, the #1 priority mission objective was a test of the heat shield on Orion for lunar return.
Orion conducted the final major maneuver of its mission, a return trajectory correction burn of its thrusters to further fine-tune its path toward its splashdown site in the Pacific.
One of the biggest learnings we had from Artemis 1 was how the thermal protection system was able to perform during reentry. We looked at the heat shield, and there were little chunks of that char that were missing. And we didn't really understand that, and we thought that wasn't predicted.
What happened is some of the heat shield material started to break off, and that we think could happen a little bit, but you don't want it to happen too much.
Our decision has been made first around safety on the heat shield, as we understand and mitigate the risks that come with spaceflight.
Sometimes in space, delays are agonizing, and slowing down is agonizing, and it's not what we like to do. But from the crew perspective, the thing that we most asked our leadership for after Artemis 1 was root cause of the ablation of the heat shield. We had an independent review team with a lot of outside experts and internal experts to look at this. So we really appreciate the willingness to take the risk to actually slow down and understand root cause, determine the path forward, corrective action for Artemis 2 and Artemis 3, so that when Victor, Christina, Jeremy, and I launch and land after a successful Artemis 2, we will look to Artemis 3 to carry the torch forward and to put humans back on the moon, and that is really our ultimate objective.
Had the crew been on Artemis 1 in the Orion heat shield, they would have been safe. This was certainly an area that we knew we wanted to test out. One reason why, of course, there were no crew on Artemis 1, so we could test out that heat shield. But we wanted to make sure we understood that problem. And we did an enormous number of tests to confirm that under specific conditions, yes, we can fly it safely. But in the future, we want to take this learning and not only apply it to safely flying Artemis 2, but to changing how we design and build the heat shield for the Artemis 3 and beyond. This is what we do. We are ready for it. This is how we work. This is how we learn.
It will be a 10-day journey going 500,000 miles, continuing to test out every bit of Orion, going around the far side of the moon, heading home through the Earth's atmosphere at over 25,000 miles per hour and splashing down in the Pacific.
The crew's going to have a horizon, they have a moon, so I feel pretty good about pressing into this opportunity.
I think NASA's at its best when it has big ideas and bold exploration. That's when the finest comes out of NASA. That's when the finest comes out of America. Their story is made up of the success of this institution that makes this country so proud.
For Orion, success means
I'm
we
reading
bring
there's
the crew
another
home.
company called
Second,
Collins.
we demonstrate what we know already is a robust spacecraft that's ready for these Artemis missions.
We want to continue to explore, we want to continue to learn, we want to go beyond, we want to go even further. And through the success of this particular mission of Artemis 2 will help spur us on for the additional exploration and discoveries that are out there for us to find.
Yeah,
Our destiny is
apparently
always to go and
that's
see what's
who
further
they
and
will
what's next.
It's our generation's opportunity to have our
push the,
own literal moonshot.
When we focus on one
design of a
thing and we
suit
focus on it
faster.
together, we can achieve anything.
It's the lesson
But
that
they're
we
already
can do more
developing suits.
together than we can as individuals. It's a new beginning. It's a rebirth of human exploration.
The question is no longer if we're going to return to the moon or reach Mars. It's a matter of when.
It starts with one flight, one crew, Artemis 2.
We all have batons, relay race batons, and they are there as a symbol of coming back from Artemis 2 and handing those batons to Artemis 3 and saying, it's your turn, go.
Well,
that is what we live
apparently
for.
they
We are
kept
ready.
developing them anyway. That's what I saw in the little research I did just now. Mm. Oh. Oh shit. Tim Cook to step down later this year with John Turnus named as successor. Currently the head of hardware engineering. Wow. Wow. The Tim Apple era is over. Beach to it, buddy. Good luck, baby. Go kick some ass. We all believe in you.
Ass will be kicked.
Good. That's my girl.
I'll leave you up as I do.
Better, baby. I'm gonna add just a little something to just up the habitation, because
That boy's a sloppy boy. Restless spirit. Get fancy.
Onion is taking over InfoWars. I thought a judge reversed that like a while ago. Oh, geez. Wow. That's amazing. Yeah, I did see that. I'm not sure quite what to make of it at this point, if I'm honest. Yeah, maybe he's not. The more I'm learning about him, the less I think he's particularly terrible, honestly. Oh, well. We'll see about that then.
Hey everybody, I got some breaking news for you. It's looking very likely that Global Tetrahedron will seize control of InfoWars in the coming days. The folks at Global Tetrahedron have asked me to step in as to run the show over there and become a big part of the future. So we're exploring. Sorry. My name is Tim Heidecker. I'm just here to let you know that I am now in charge of InfoWars. It's an honor to take over the reins and chart a new path towards the future. We're looking forward to relaunching the site soon in the next coming months, and we're not really sure what we're going to do with it. We're talking about all sorts of ideas. We were playing around with it being a real estate broker service or a cryptocurrency exchange market, a place to store pictures, almost like a Dropbox account. Not sure, a lot of ideas, but very excited to take this on. And just want to wish everyone, extend a hand of friendship and grace as we proceed through this process. It's not going to be easy, but I can assure you that we have our best intentions in mind.
Well, hopefully
we are in the city of brotherly love, and I want to extend that sentiment to all our friends over there, longtime fans and consumers of the InfoWars products. We've got some exciting products coming as well. We're working with a company that will enable you to turn your urine into gold. So stay tuned for more information about that, and stay with us. Stay updated on InfoWars for more information as this story develops.
Jeez. Oh, shit. Didn't say. How many verbals you can hold? Piss to gold. That's the key, okay? It. Slash module deflate have curb performance. Okay. Okay. That's why it has to be inflated. Hmm. Okay. Another one. What do we got? It was only a matter of time. Only a matter of time. To be quite frank with you. Tim Apple stepping down. I'm not sure, honestly. All right, guys. I'm ending the early stream for now. I'll see you guys in a few hours. We're gonna chill, talk politics, do that fun stuff. Everybody have a beautiful time. See you later. Bye.